the neutral conductor is required to be counted as a current carrying conductor. Let's delve into the applicable code sections. NEC section 310.15b4 states that if the neutral conductor carries only the unbalanced current between the other conductors, it is not required to be counted as a current carrying conductor under this section. However, NEC section 310.15b4 provides a contrasting scenario. Neutral conductors that are connected to the grounded circuit conductor on the supply side of the service disconnecting means and extended to grounding electrode shall be counted as current carrying conductors. Considering the specific application to data center servers, the neutral conductor is connected to the grounded circuit conductor on the supply side of the service disconnecting means and is extended to a grounding electrode. Therefore, NEC section 310.15b4 applies. This dictates that the neutral conductor must be counted as a current carrying conductor. The reasoning behind this lies in the dual purpose that the neutral conductor serves. Firstly, it carries unbalanced current between the other conductors. Secondly, it provides a path for fault current to flow back to the source. Since the neutral conductor is performing both of these functions, it must be counted as a current carrying conductor under NEC section 310.15b4. Therefore, when calculating the number of current carrying conductors for the 12 dedicated circuits supplying the 30 amp 120 volts twist lock receptacle for the data center servers, the neutral conductor must be counted. Let's further clarify the context of current carrying conductors and their implications within electrical systems. When designing and installing electrical systems, particularly in environments like data centers where reliability and safety are paramount, it is crucial to accurately determine the number of current carrying conductors in a circuit. This count directly impacts the ampacity, or current carrying capacity, of the conductors, as well as the required deriving factors to ensure safe and efficient operation. Ampacity refers to the maximum amount of electrical current a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code, or NEC, provides tables and guidelines for determining the ampacity of various conductor types and sizes, taking into account factors such as the insulation material, ambient temperature, and the number of conductors bundled together. When multiple current-carrying conductors are grouped together in a raceway, cable, or bundle, the heat generated by each conductor can raise the overall temperature within the enclosure. This increased temperature can reduce the ampacity of the conductors, potentially leading to overheating, insulation damage, and even fire hazards. To mitigate these risks, the NEC requires ampacity derating when the number of current-carrying conductors exceeds a certain threshold. Derating involves reducing the allowable ampacity of the conductors based on the number of conductors present. The specific derating factors are outlined in NEC Table 310.15b3, which provides adjustment factors for various numbers of current-carrying conductors. These adjustment factors are applied to the base ampacity of the conductors to determine the allowable ampacity under the given conditions. Now let's circle back to the specific case of the 12 dedicated circuits supplying the data center servers. Each circuit consists of one phase conductor, one neutral conductor, and one equipment grounding conductor. While the equipment grounding conductor is not considered a current carrying conductor, the phase and neutral conductors are. Therefore, in this scenario, there are 2 current carrying conductors per circuit, resulting in a total of 24 current carrying conductors for the 12 circuits. With 24 current carrying conductors bundled together, significant ampacity derating will be required according to NEC Table 310.15b3. This derating will reduce the allowable ampacity of the conductors, potentially requiring larger conductor sizes to meet the 30 amp load requirements of the servers. In addition to ampacity derating, it is also essential to consider voltage drop in the circuit conductors. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its impedance, or resistance to the flow of current. Excessive voltage drop can negatively impact the performance of electrical equipment, causing them to operate inefficiently or even malfunction. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, It is necessary to select conductors with adequate size and conductivity. Larger conductors have lower resistance and therefore experience less voltage drop. The length of the circuit also plays a significant role in voltage drop. Longer circuits will experience greater voltage drop than shorter circuits with the same conductor size and load. In data centers, where circuits often run long distances to reach servers located throughout the facility, voltage drop can be a significant concern. Careful planning and conductor selection are crucial to ensure that voltage drop remains within acceptable limits. Furthermore, it's important to understand the different types of neutral conductors and their roles in electrical systems. In a single-phase, three-wire system, such as the one described in the question, the neutral conductor serves as the return path for current from the load back to the source. It also provides a reference point for the voltage, ensuring that the voltage remains stable and balanced. In a balanced three-phase system, the neutral conductor carries little or no current because the currents in the three phases cancel each other out. However, in an unbalanced three-phase system, where the loads on each phase are not equal, the neutral conductor will carry the unbalanced current. The amount of unbalanced current that the neutral conductor carries depends on the degree of imbalance in the system. In some cases, the unbalanced current can be significant, requiring the neutral conductor to be sized accordingly. As mentioned earlier, NEC section 310.15b4 states that the neutral conductor is not required to be counted as a current carrying conductor if it carries only the unbalanced current from nonlinear loads. Nonlinear loads are electronic devices that draw current in a non-sinusoidal waveform, such as computers, servers, and electronic ballasts. These devices generate harmonic currents, which are multiples of the fundamental frequency of the power system. Harmonic currents can cause significant heating in the neutral conductor, even in a balanced three-phase system. To mitigate the effects of harmonic currents, it is common practice to oversize the neutral conductor in circuits that serve nonlinear loads. This allows the neutral conductor to carry the harmonic currents without overheating. NEC section 220.61 provides guidance on sizing the neutral conductor for nonlinear loads. In the case of the data center servers, which are considered nonlinear loads, it is important to carefully consider the harmonic currents generated by the servers and to size the neutral conductor accordingly. Now let's discuss the importance of proper grounding in data center electrical systems. Grounding is the process of connecting electrical equipment and circuits to the earth, providing a low impedance path for fault current to flow back to the source. Grounding is essential for safety, as it helps to prevent electric shock and to protect equipment from damage. There are two main types of grounding systems: the equipment grounding system and the grounded conductor system. The equipment grounding system provides a path for fault current to flow back to the source in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as the metal enclosure of an electrical appliance. The equipment grounding system consists of the equipment grounding conductors, which are typically bare or green insulated wires that connect the metal enclosures of electrical equipment to the grounding electrode system. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, crown plates, or metal water pipes, that are buried in the earth and connected to the equipment grounding conductors. The grounded conductor system, also known as the neutral conductor system, provides a reference point for the voltage and helps to stabilize the voltage. The grounded conductor is typically a white or gray insulated wire that is connected to the neutral point of the power source. In a properly grounded electrical system, a ground fault will cause a large amount of current to flow through the equipment grounding conductor, tripping a circuit breaker or fuse and energizing the circuit. This helps to prevent electric shock and to protect equipment from damage. In data centers, grounding is particularly important due to the sensitive nature of the electronic equipment. Data center equipment is susceptible to damage from voltage surges and other electrical disturbances. Proper grounding helps to protect this equipment from damage and to ensure reliable operation. The NEC provides detailed requirements for grounding electrical systems in Article 250. These requirements cover the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal enclosures and other conductive parts. In addition to the NEC requirements, there are also industry standards and best practices for grounding data center electrical systems. These standards and best practices often go beyond the NEC requirements and provide more specific guidance for grounding data center equipment. For example, some data centers use isolated ground systems, which provide a separate grounding path for sensitive electronic equipment. Isolated ground systems help to minimize noise and interference in the grounding system, improving the reliability of the equipment. Furthermore, regular testing and maintenance of the grounding system are essential to ensure its effectiveness. Grounding systems should be inspected periodically to check for loose connections, corrosion, and other signs of damage. Grounding electrodes should be tested to ensure that they are providing a low impedance path to ground. Any problems with the grounding system should be corrected promptly to maintain the safety and reliability of the electrical system. In summary, when dealing with 12 dedicated circuits, each with a phase, neutral, and ground, supplying 30 amp 120 volts twist lock receptacles for data center servers, the neutral is generally considered a current carrying conductor according to NEC 310.15b fork. It is important to account for this when calculating conductor ampacity and applying directing factors. This ensures proper electrical design and safe operation of the data center.